So hi everyone, and thanks for showing up for this 6th week at Atom. So I will be talking about tropical moduli spaces for the two lectures. Let me start by telling you keywords and plan for the lectures. So this is going to be so the keywords are the first things that you see in my screen. So I am an algebraic geometer who works mostly in moduli spaces, and I like to see compactifications of moduli spaces, and you can see the list of my favorite ones here in the slide. So, so my point of view, so I got into tropical geometry actually by trying to understand the generations of so how could a compactify, so how can tropical geometry help on understanding degeneracy data, which we try to parameterize when we deal with a compactified moduli space or a compactification of a moduli space. So this is the plan. So we start. So I want to get into tropical geometry. So in these lectures, from moduli spaces, and in particular by trying to understand how can we use tropical moduli spaces to give parameter spaces to compactifications of moduli space. So today it's going to be about the moduli space of curves and the moduli, and basically that's it. So the moduli space of curves, then as I already mentioned, the compactification of the moduli space of curves by stable curves and the version with marked points. I will start by talking to you about the classical moduli space, and then I will tell you about the tropical version and how can that help us understand the original moduli space itself. And then on the talk in Wednesday talk, I will be telling you about these other moduli spaces. So the moduli space of a billion varieties, Jacobians, which are in particular case, and the Torelli map, which will be a way to link the moduli space of curves and the moduli space of a billion varieties via Jacobians, as you will see. And yeah, I'm going to talk about the tropical version of this. But this is going to be on Wednesday. So possibly the Wednesday talk could be a little bit more technical than what I will be doing today. All right, so I will start from the very beginning and telling you a little bit about moduli problems in algebraic geometry. So as you know, in algebraic geometry, we usually try to study classes of problems of algebra geometric problems by studying parameter spaces for this class. So what do? We fix a certain type of algebra geometric class of object that we want to study, and we try to study a parameter space for this, which as you know, in algebraic geometry, quite often happens to be, again, an algebraic variety or a mild generalization of that as which is going to be usually a moduli stack or yeah. And so maybe in the first lecture of algebraic geometry, that in the first course of algebraic geometry, maybe the first example of a moduli space that we all see is the moduli space of hyperplanes in projective space. So if we want to think of them as a moduli space, what can we do? So we try to understand what are hyperplanes, what are hyperplanes and what is the data that we have to give in order to define a hyperplane. And of course, so a hyperplane is defined by a linear equation, and the linear equation is defined by setting up the scalars the coefficients for the variables, and then two such linear equations will define the same hyperplane if and only if they if and only if this tuple of coefficients differ by some non-zero scalar. And so we see that again, hyperplane in so the set of hyperplanes in PN can be parameterized by PN itself. So this is a way to see this set of algebra geometric objects as a moduli space again. So this PN is usually thought of as the dual projective space. So this is the first very easy example of a moduli space that I think all of us saw in our first course of algebraic geometry. And then the one that maybe that certainly me heard about more is the moduli space of curves. So first we think about the moduli space of smooth curves of given genus up to isomorphism. So we want to parameterize smooth projective curves up to isomorphism. So you might want to think of these as compact Riemann surfaces if we are over C. And so once we fix the genus, the first example to consider is the moduli space of rational curves. And you know, like all small curves of genus 0 are like P1, are isomorphic to P1. So the moduli space M0 would be just a point. And then if we move to genus 1, we also see that an elliptic curve, so a genus 1 smooth curve, is defined by the J invariant. So we can think of the moduli space of curves of genus 1 as just an affine line. So this is an algebra. This is an algebraic variety which will be giving a parameterization for our moduli space M1, or more or less. And then if we move to genus at least 2, then this is harder, and but it's also very classical, and it's the work of Riemann in the 19th century. So he oversee at least. So we have this theorem due to Riemann. So the space of non-isomorphic complex structures definable over a compact connected topological surface of genus at least 2 has complex dimension 3G minus 3. So this is this is maybe the first paper on moduli theory, and I think also where the word moduli was introduced as well. So this is the starting point, and now let me just be a little bit more, just a little bit more precise. So by discussing with you what is a moduli problem. So how do we set up a moduli problem precisely? So we start by fixing a category C of algebra geometric objects and morphisms among the objects. And we consider a moduli functor associating to a scheme S the set of families of objects in the category over S. So let me just write down something. So I will write the functor over here. So we have FC from the category of schemes to the category of sets. And we so this is the moduli functor of families of objects in C. So over S, I will just be representing families over S. So I will see this as some morphism in C over S. And so what do we want? We want this functor to be representable. So we say that moduli space MC is a fine moduli space for this functor if this space is a representative for the functor. And so how do I think of this in the beginning? So I think of some moduli, some family, some family in the category I'm thinking of, which for me it's very often the category of curves. And I think of a moduli space for this as some bigger object where I see this thing as just a little something which is parameterizing me, the whole family. So you know, so saying that this moduli space is a representative for the functor means that then we would have FC to be FC of S to be in bijective correspondence with the homomorphisms over S. No, homomorphisms over your representative, so over MC. So the functor would be representable by this object MC if the functor FC could be the functor OM over, so here it would be S over MC. And this is the ideal situation that we would want in order to have a really nice moduli space. But however, as probably you know, this is not possible to have most of the times. And this is easy to see if you think that there are maybe isotrivial families of objects in your category. So meaning that you might have families which are non-trivial as a family, as a morphism, meaning that they are not of the form basis times a fiber, but they could be still, all of them could have isomorphic fibers. And then you see that there could be no way for you to distinguish between such an isotrivial family and a trivial family if you have this kind of phenomena. Yes?
Why do you want C to be a category? Why do you need morphisms between the objects of interest?
Sorry, what?
Can you maybe say what C should be? Oh.
Well, I'm just saying in general. So this could be applied to different situations, and I don't know. Maybe I'm thinking about C to be. So for today, C is going to be the category of curves and morphisms between curves, and then I would have to specify which kind of morphisms do I need, of course. So I would say flat morphisms or projective or something. I don't know. It depends on the thing I want to parameterize. Okay. I don't know. So now the point is that so we might not have this ideal situation to hold if we want the representability of the functor by space in the same category at least that we are trying to work with. And so there are two situations that could be a partial solution, at least for this problem. So one thing that we could do is that we ask for a coarse representative for the functor. What is this? So this means that, so let me just write down. So this means that instead of having this bijection between the FC of S and the homomorphisms, we could ask for FC of K to be in correspondence with the homomorphisms of K onto MC, where K would be just an algebraically closed field. And then the second thing is that instead of asking in general for any S that we have that we have a bijection between FC of S and the homomorphisms, we could ask that there is a natural map only on this direction. So an object, a family over S would give rise to a morphism onto the moduli space, but two families could give rise to the same morphism. So this is one possibility. So this would be the coarse representative. And then the second thing is that we could ask for a representative, but in a bigger category, so the category of algebraic stacks, which is something that we usually do and makes our life much easier in many situations. And yeah, this will be the situation for the moduli problem of curves. So what we will see is that there is a moduli stack MG representing the moduli problem of curves, and a quasi-projective space representing the moduli, a quasi-projective moduli space, which is a coarse representative for the stack. So let me
What is an algebraic stack?
Yeah. So what is an algebraic stack? So I will not give the precise definition of an algebraic stack. So let me just say that it's a generalization of the notion of scheme. So each scheme is an algebraic stack, and so it's a categorical version of a scheme. So what it's a way to see instead of thinking of the objects, you think of morphisms. So an algebraic stack basically is a category fibered in groupoids where you see over schemes, for instance, and where you ask for some chief theoretical conditions to hold, and then the algebraicity comes from the fact that you ask for the existence of an atlas coming from a scheme or an algebraic space. But actually, so I will not go too much into detail on this. If someone has specific questions, then maybe we could discuss afterwards, because I just want to get into more or less the idea. So what we will have in the moduli space that we don't have in the moduli scheme is that, so we will have the possibility to encode as well the families, the isotrivial families as different objects, instead of the situation we would have if we were dealing with a base scheme. So isotrivial families will be different from trivial families in the end. So we will not, so in other words, we will not mod out by these automorphisms of the families. Okay, why? So this is not, this didn't change, right? You still see the other, let me see. So this somehow, it just stopped the sharing. So now it's okay, right? Okay, so now let's go for the compactification. So I started telling you about that. The idea is that we use tropical geometry actually to as some way to parameterize the degenerations, at least, or at least it's a way to see it from the tropical moduli spaces. And so MG is not compact, and this is a problem. So MG, so now I am talking about the moduli space of curves. So it's not compact. It's easy to see that you could have families of curves over non-complete bases that you could not complete over smooth curves. So let me just do some drawing. So imagine a family of curves which over infinity degenerates to some nodal curve. So this is possible to have, and also it's unavoidable. So it's easy to see that that sometimes if you have a family of smooth curves over a puncture disk or this situation and a fine curve, if you want to complete it over infinity, you would have to insert a singularity. So this is, if you want a compact space, then it's not enough to consider smooth curves. And so there is this remarkable work by Deligny and Mumford in '69, who solved this problem by considering compactification of MG, which is denoted by MG bar, and this has the important property of being modular. So what's the meaning of this word? So it means that the points of mg bar, which is going to be some bigger space containing mg as a dense as a dense subspace. So the boundary points will also parameterize algebra geometric objects. So you see, so according to the linear Mumford construction, points in mg bar will parameterize stable curves of given genus. And what is a stable curve? So a stable curve is a projective connected nodal curve which could admit mild singularities. So the mildest singularities, the mild singularities are these nodes. So it's not smooth, but you could have only the simplest singularities that you can think of, which is these nodes. And if you want that, so if you have to ask for some stability condition, otherwise you would get something which is not a finite type. And you could ask that the automorphism group of your curves would be finite, and this is equivalent to the condition I just wrote here, which is that for each subcurve of your curve, you ask for twice the genus of the subcurve minus 2 plus the number of points where the subcurve means the rest of the curve is at least 0. So it's easy to see that these two conditions are equivalent. Okay, so and now we start to see something which may be more tropical, which is we start to see that these stable curves, so the curves that we find in the boundary of mg bar, they can be, so their topology can be encoded using graphs. So we can use graphs to encode the topological type of stable curves, and this is what I want to describe now. So how do you do? So we so is there some question?
What's the difference between stable and semi-stable?
What's the difference between stable and semi-stable? Yes. So so stable is so you can see this in oh yeah. So if you can just so that there are so one way to see this is that so maybe here you could just ask for this to be bigger than -1. Maybe this would be enough, right? I think yeah. So I think this would be a way to define it. Semi-stable would be, instead of asking to be for this number to be bigger than 0, maybe you could just ask for to be bigger than -1. I think this would be enough. All right, so this would be, so this is a condition that you find in when you try to construct, so these spaces are constructed using GIT. One way to construct these spaces is using GIT, and the stable objects would correspond to GIT stable objects, and the semi-stable would correspond to GIT semi-stable objects. So here you would have in the semi-stable situation, you would be able to have things like this, which are, so you could have something which is a P1. Do you see this writing here that I'm drawing in the end or not?
No, we don't see that.
No, you don't see it. Okay. So you could have in the semi-stable situation, let me write like this. In the semi-stable situation, you could have something like this. So a P1 meeting the rest of the curve in only 2 nodes. So if you see, so this will violate the inequality I wrote here. But if you replace this with -1, I think it would work. All right. So so now let's use graphs to encode the topological type of stable curves. Actually, we can use graphs to encode topological type of any nodal curve. But our interest here was going to be, it will be the one for parameterizing stable curves, and then we see how can we see the stability from a graphical point of view. So we will just do the usual thing. So we take irreducible components of the curve, and this will correspond in the dual graph to vertices in the dual graph. And then we will describe nodes using, so the nodes will be described using the edges in the dual graph. So if you have a node between two different irreducible components, the corresponding edge will be incident to the corresponding vertices. So incident to the corresponding vertices. So let me just do some pictures here. So imagine that you start by, so let's take genus 2 here, and imagine that you like to see the curves from a Riemann surface point of view. So take a smooth Riemann surface. I like to describe this like this, just a curve and two to mean the genus. And then the dual graph is going to be very easy. It's just one vertex. And so actually, let me say that the graph is going to be with weights. So here I will put weight 2 in the vertex to mean that the corresponding component as genus 2. And then I want to see the stable graphs, the stable curves, which will be obtained by degenerating my original smooth curve. So for instance, imagine that you shrink over a circle here, and then you end up with the curve like this. So you have a node here. So for me, I want to see this like this, as two smooth genus 1 curves meeting in one node. And the dual graph is going to be then two vertices of genus 1 and one node between these two vertices. And I could, of course, generate more. For instance, I could shrink this circle here, and then I would end up with something like this. So in my curve description, this is going to be like this. So I created a loop, so an internal node. Yes, in the dual graph, this is going to be a loop, so an edge that is double incident to this vertex. And let me just draw something more degenerate. So imagine that I shrinked in the beginning other loops. I could end up with something like this. So two Riemann spheres, which are linked one to the other in 3 points. And this is going to be, in my point of view, just two genus 0 curves. I don't write the genus if it's rational. And the dual graph is going to be then two vertices and 3 edges between these two vertices. And I will omit again the weight in the vertex because it is just 0. All right, so there are no questions about this. Okay, so these are the dual graphs.
The last one should be drawn slightly differently, right? I mean, this seems to have 4 components.
Sorry?
The last one you drew on the left lower corner, I think.
Oh yes, sorry. The Riemann surface. Sorry. Yes, sure. I just yeah, like this maybe. Well, I don't know. How should I do? And then this could be like this, right? Yeah, so this is one component and this is the other component, and these are the 2 holes. Yes, thanks, Martin. Yeah. All right, so it's okay now? Okay. Okay, so now let's move to the moduli space of curves with marked points. So what are we doing now? So now we will enrich our problem by considering not only curves, but we will try to parameterize along with the curves distinct points in the curve. So this is often useful from different points of view. For instance, this is important in enumerative geometry. If you want, you could imagine that you could consider that you would like to have a parameter space where not only you parameterize certain classes of objects, but also you want to deal with situations where you have points varying continuously, and you want to understand the geometry of all of these. And so this is the situation where we consider MGN. So this is going to be moduli space for a smooth curve of genus G, together with n distinct points, which are labeled. And again, of course, MGN is not compact. Here we have two different kinds of phenomena. So we have the fact that the curves can degenerate as it was the case in MG, but we can also have the points colliding, for instance, and then we have to do something about it in order to be able to distinguish the points. And also we have to deal with the fact that we don't want points to degenerate to singular points. And these are two situations that we have to deal with when we want to describe a compactification for MGN. So a compactification for MGN is MGN bar, which was, this MGN bar, which was constructed by Knudsen, was a student of Mumford in the 80s. And this is a moduli space again, a modular moduli space again, meaning that the points in the boundary will again parameterize algebra geometric things. So we will be able to distinguish, to define the points in the boundary as points which have a modular meaning. So what are these n-pointed stable curves that we find in MGN bar? So an n-pointed stable curve is just a projective connected nodal curve of genus G, together with n distinct smooth points. So you see smooth points in the curve, with again the stability condition, which is again equivalent to having to requiring that the automorphisms of the curve, which fix the markings, should be finite again. So here, a way to see this is this thing. So we ask for any subcurve of the curve to satisfy this inequality, meaning that twice the genus of the subcurve minus 2 plus the number of special points on the subcurve to be at least 0. And here, by special points, I mean either singular points and together with markings. All right, so here you see that, and also in the situation where you don't have markings, that if you have a subcurve with genus at least 2, then this inequality will tell you nothing, right? So if you have a subcurve of genus at least 2, this will be already positive. So you have no requirement. So the requirement here is if you have P to be isomorphic to P1. So if you have a rational subcurve, then this condition will be saying to you that your P1 has at least 3 markings, which is, as you know, what you have to ask for in order to fix your P1. So meaning that your P1 could have or some singularities, meaning that it meets some other points, or that you could have markings in your P1. So for instance, if this is a P1 with 2 markings, this is still not stable. So if you could, for instance, have this this thing here. So if you have a node, then this would be stable. And the other situation is if you have if the genus of E is equal to 1, then you have an elliptic smooth curve, and then you ask for the subcurve to be at least to have or a marking or a node.
Is the
this
of points allowed as an automorphism?
Sorry?
If you switch P1 and P2, is this allowed as an automorphism?
Yeah, well, you have to fix the points. No, you have to fix. So the points are labeled, yes. So for instance, if you have a P1 with, so if you have a P1 with 3 points, this would have no automorphisms. Yeah. Okay, so let's go on. So let me just, before I go to, I try to tell you something about the tropical point of view of the boundary. Let me tell you some facts about the moduli spaces. So either in the space, even for the coarse moduli spaces or the stacks. So there are moduli stacks, MGN, and its compactification. So I will use, as usual, this notation. So the calligraphic letters for the stacks and the usual letters for the moduli spaces. So there are moduli stacks representing the moduli problem for stable curves with marked points or not. And these are smooth, the Linear-Mumford stacks of dimension 3g minus 3 plus n. Yeah, the compactification is proper. And they have coarse moduli spaces, which will be this MGN space, which is a quasi-projective variety, which is a moduli space for the moduli stack of smooth curves. And there is a coarse moduli space, which is a projective variety, which is a coarse moduli space for the moduli stack of stable curves with marked points. Yeah, so there is there's also a sentence here that I will be explaining later. So this compactification is toroidal, meaning that the way, and the reason why I want to mention the stack here, even if I'm not telling you very precisely what that is that it's important to consider the stack in order to have this fact to hold, because afterwards, in the end, when we want to relate the compactification of the moduli space with the tropical moduli space, it's important that you have that the space you started with is compactified in a toroidal way, meaning that locally it's like a torus inside a toric variety, more or less. And we have a description of the boundary of this compactification, which will be done via stable graphs, via a partially ordered set of stable graphs, which will be the dual graphs of our curves that we already saw. Yeah, so let me just complete the dual graph situation for the case where we have legs, because we didn't see that yet. So for instance, imagine that we have a curve like this. Imagine that we have a curve like this. So this is a genus 1 curve, this is a genus 2 curve, and we have a marking here. This is going to be P1, this is going to be P2, this is going to be P3. And then the dual graph of this, as we already saw for the situation where we have no markings. So this is going to be 2 vertices, and then we have 2 nodes between the two components, so 2 edges between the 2 vertices, and we have a loop here. And then we have the markings that we will encode with the legs. So this is going to be a first leg in this component, and then we have 2 legs in this other vertex. All right, so this is the dual graph. If we want to parameterize also the markings, we just include the legs in the inserting them in the corresponding vertices for the according to the vertex that corresponds to the reducible component where the point is. Okay, so now let's see this from the point of view of graphs. So what is a weighted stable graph with legs? So this is just a pair GW, where G is a connected graph with legs, and we have this stability condition. Sorry, we have a stability condition which which needs this weight function here. So we have also a weight function from the vertices to the set of non-negative integers, and the stability condition is this one. So we ask that for all vertices in G, the weight of the vertex minus 2 plus the degree of V, meaning the number of edges incident to V, plus the number of legs incident to V is at least 0. And we say that the genus of a graph with such a weight function is just the first Betti number of the graph plus the number, plus the total weight. So for instance, let me draw something here. So if we have, so this is a 2-vertex graph with weight 1, 1. So what's the genus of this graph? So the genus of this graph is going to be the first Betti number of the graph, so which is 2, right? We have 3 edges and 2 3 edges and 2 vertices. So this is genus first Betti number 2 plus the total weight, which is again 2, and so this would be genus 4. And this respects stability, right? Because so again, if you have vertices with weight at least 2, this is just asking nothing. And if you have vertices of weight 0 or 1, this means the same condition that we saw before for the stability condition on nodal curves. So this is exactly what we see here, that the definition of weighted stable graph of genus G and N legs exactly corresponds to saying that these graphs are dual graphs of stable curves of genus G and N markings. So so the definition is done in such a way that there is this exact correspondence. All right, so what can we do with these stable graphs? So the first thing is that we will consider inside our parameter space for
what
the
is the absolute value of W?
So it's the total weight. So this is just the sum over all the vertices of G of the weight of V. All right, so as in this situation here, in this example, this would be the total weight. Yeah, maybe I should have chosen some example where the different weight was different of the first Betti number, but anyway. So yeah. So what can we do? We can consider inside the moduli space of stable curves with markings.
W times W of V in the definition is one question.
In the definition of what? Of the weight?
Yeah, I think so.
Of the genus?
Yeah.
Oh, here. Yes, sorry, yes. In the definition of stability, right, yeah, thank you. Yes, this should, yeah. It's twice the weight, sure, yeah. Sorry about this. Yeah. Okay, yeah, so it's twice, yes, that's why if we have weight equal to 0 or if we have weight at least 2, then this condition will just say nothing. And yeah, and if we have weight equal to 0 or 1, yes, the idea is exactly that we describe using the dual graph the stability condition for stable curves. It's this. Yeah. So sorry about this, and thanks for pointing this out. Okay, so now we consider the inside MGN bar, so the moduli stack or space of curves of stable curves of genus G and then markings. We consider a locus, which we will write using MG, the graph, of curves with dual graph equal to G, and maybe using the notation before. So if we have weights, I will also write like this. All right, so it's a model. So sometimes I think of the graph already to be weighted, but here I wanted to stress the fact that we have also a weight function. So yeah, so this is a moduli space. So this is this is the locus inside our space, parameterizing curves whose dual graph is of type GW. So this is a locus inside the moduli space of curves, and it will be very very important for us in our description of the moduli space. So one sees that the closure of these locus inside the moduli space of curves consists of curves which can be smoothed to curves in MG. For instance, imagine this situation here. So you have genus to curve, and you in the closure of, so this is inside the locus of this graph. So this is inside the locus parameterized by this graph. And if we consider the generation where we shrink this link, we're gonna end up like this. And what we see is that in the dual graph, what we replace this loop, we replace this one with a loop. And so this is a degeneration that happens in the moduli space of curves. And so this should be in the closure. So this curve should be in the closure of the strata where this curve lives. On the other hand, graph theoretically, what we see is that we can see the graph parameterizing the smoother curve as obtained by contracting something from the graph that corresponds to the most degenerate curve. So let's define contractions of stable graphs now. So, and see that this is something that we can have so that we can understand closures of these locus of inside MG parameterizing curves with some specific dual graph, and we can parameterize the closures of these locus using using contractions of graphs. So let's see. So take a graph, a weighted graph GW, and we say that another graph G prime, W prime is a specialization of the first one, if it can be obtained by the other one by a sequence of contractions and automorphisms according to the rules that I describe here. So if you have a graph like this with two legs, two weights, so imagine that we are contracting this edge over here. In the end, what we see is that the two legs just get incident to the vertex that you get in the end, and you just sum up the weights. And the other situation that you could have is that you could contract a loop, as we saw in the previous example. And then what you get, what you have to do is in the contraction, you include the weight, and you increase the weight by 1 in order to encode the fact that you just contracted the loop. So there's going to be the exercise session tomorrow. And one of the exercises that you can do is to show that the genus of the graph, that genus are preserved via the contraction. Yeah, so there's lots of things that I am not explaining very well, and that will be, I hope, better understood in the exercises tomorrow. So what we can see is that in the closure of the locus of curves with some dual graph, here I forgot about the weights. We see that this is described using using other strata. So the closure of the stratum corresponding to a graph and a certain weight function consists of all strata M, G prime, W prime, such that G prime, W prime contracts or specializes to GW. Okay, so now we can, just to be more precise, we can define using stable graphs of a fixed genus and number of legs, we define a category, which is the category SGN, the category of these whose objects are weighted stable graphs of fixed genus and legs, and with morphisms determined by specialization. And we see that this has a partially ordered set structure. So this has a poset structure. And according to the observations that we just did, the boundary of the compactification, so the compactification admits a stratification which is governed by this poset. So meaning that, so what's the stratification? So the boundary admits, so it's a disjoint union of strata like this, of strata of this, of strata of the form MGW, where GW is just some stable graph, and the closure of each stratum is the union of other strata of lower dimension. And okay, so yeah, I think I'm gonna have little time to describe tropical curves, but I'll try to do my best. So now we go to introduce briefly tropical curve. So what's a n-pointed abstract tropical curve? It's a triple GWL. So where GW is just a weighted stable graph with n legs and genus G, the ones that we just saw in the previous slide, and that we call the combinatorial type of C. And L is a length function on the edges, and such that if you, it's a length function, so you will assign a length, a positive length to each edge, and you say that the lengths of the legs are infinity. So in such a way that the graph without the legs becomes a metric space. So this is this corresponds, this notion. So if you see that if you consider tropical curves up to tropical equivalence, then what you get is this notion of, so you always you can get to this definition of abstract tropical curves. So this will correspond to tropical curves up to tropical equivalence. And now, how can we construct a parameter space for tropical curves? So we fix a combinatorial type. So we fix a combinatorial type for the curve, for the tropical curve, and you just allow for the edges of you just allow for all types of lengths that you can have in the edges of your curve. So you consider the lengths, the possible lengths in all tropical curves of this combinatorial type. And so what we can define a cone, which is going to be a cone parameterizing the lengths of tropical curves, a certain combinatorial type. So you see that tropical curves, a certain type, will correspond to this cone modeled out with the automorphisms of the graph, of the weighted graph. So for instance, if you have a situation like this, so this is the type of the curve. So you have one edge here and another edge here. So you have two lengths to parameterize. So you start with considering R2.
Is the length 0 allowed?
Sorry?
Is length 0 allowed?
No, it's not allowed. Yes, it's not allowed. It's bigger than 0. So this is open. And then you see that here there is an automorphism of your curve, which corresponds to switching the edges. They are just the same. So in the end, you get a parameterization of all tropical curves of this type if you just consider these, quotient. This would be open. And so you see that if you vary GW among all stable weighted graphs of genus G and N legs, oh, here I forgot about the legs, you would get, so you will have a set which will parameterize your moduli space of tropical curves. So now, what can we do? So now we can try to give this space, this set, a little bit of more structure. So this should be topology and structure of the moduli space of tropical curves. So meaning that if we want this set to make also sense from the point of view of encoding the degenerations of tropical curves, we should say that in the closure of each cone, we should find the cones that correspond to specializations. So the closure of each cone which would correspond to specializations of the curves that you started with. So in the previous example, we have this cone, open cone, and this would be the moduli space for this curve. And you see that if we contract, for instance, this edge, you're going to end up with this curve, and this would be parameterized by just closing this cone over here. And this would be this one, the vertex here would parameterize just the further degeneration where you also contract the loop. So this is the idea, that you construct a moduli space by topologically saying that the way to glue the different cells should be should describe this degeneracy phenomena. So more precisely, one way to define MGN drop is as a generalized cone complex with cells given by these cones, is that you take the limit over this category, which had the poset structure I allowed it before. And if you take this limit of these cones, then you end up with a generalized cone complex with these cells, and that which will be our object. So the moduli space of tropical curves is defined as a generalized cone complex like this. So this is, so also in the exercises tomorrow, we'll see some of these properties. So we'll see that this has pure dimension equal to 3G minus 3 plus N. You can also show that this is a normal laws of topological space. There is a compactification of these, which is just allowing for the edges of the to take value infinity, and also about connecting to the first part where we discussed a bit about different stages of solving a moduli problem. So there is a stack theoretical version of MGN drop, which was constructed by Cavalieri, Shan, Ulrich, and Wise, and which somehow solves part of the problem of having a universal family for MGN drop as well. All right, so let me just finish by saying a few words about how we come back. So maybe I can start on Wednesday lecture by telling you a little bit more about this picture if you wish, but we can come back to the so let me just tell you that there is a very, very beautiful work due to Abramovich, Kaporazov, Payne, who showed that actually the way that the generalized complex structure of MG and drop really is something that comes intrinsically from the geometry of the compactification of MGN inside MGN bar. So consider MGN inside MGN bar. So as I said, this has a toroidal structure. And then using the geometry of this compactification, you can construct the Berkovich analytification of the moduli space, MGN bar analytified. So this you maybe saw in Enrica Mazon's lecture 2 weeks ago. So you can consider this analytification. This comes with a topological retraction to generalized complex. And then in this work, they showed that this skeleton sigma of the toroidal compactification is really isomorphic to the tropical moduli space. So yeah, I think this is really a beautiful result that was then generalized to other moduli spaces and has been used to different things also, including understanding MG, the classical spaces as well. Okay, so just let me say, so this was just revisiting the keywords I started with. So the way to go from algebraic geometry to tropical geometry is the tropicalization map that I didn't have time to describe. And the way that the moduli space MG sits inside the compactification is something that we can see by carefully looking at this topological retraction that will allow us to describe the skeleton of the compactification. So the skeleton of the compactification has a tropical modular description. Has a tropical modular description. That's a way to, so that's what the story I wanted to tell you. Okay, so I'm finishing here. Now, if there are some questions, I'm happy to answer.